For as long as we've been going to space, we've relied on one thing to communicate: electricity flowing through copper wires. But that's all changing. A huge shift is happening, and it's all about rebuilding our future in space, not with electricity, but with light. So, let's just get right to it. The biggest question in space technology right now is this one: how do you do it all? And the answer, it's not just about building bigger, better rockets. No, it's about going way deeper and totally rethinking the very foundation of how we communicate. And to really get why this change is so huge, you first have to understand just how tough the challenge is. The constraints of working in space are just enormous. Get a load of this number: $20,000. That's what it costs to launch one single pound. Think about the weight of a football into orbit. When you're dealing with numbers like that, suddenly every single ounce, every gram becomes unbelievably precious. Yeah, that insane cost is exactly why engineers are obsessed with something they call the SWAP problem. It stands for size, weight, and power. And the goal is simple. You have to make everything smaller, lighter, and more energy efficient. For decades, though, one specific thing has been a huge roadblock. And what is it? You guessed it, good old traditional copper wiring. Yep, the same stuff that's been powering our electronics for, 100 years? Well, up in the harsh environment of space, its weaknesses are really starting to show. It's become a major bottleneck. And this really lays it all out, right? Look at the difference. Copper, it's heavy. The signal gets weaker the further it goes. And it's super vulnerable to all the electromagnetic interference you find in space. But fiber optics, it's a whole different ballgame. They're feather light, the signal stays perfectly strong over incredible distances, and they are totally immune to all that interference. It's not even a fair fight. Okay, so where does this revolution begin? Well, you might think it starts up in orbit, but nope. It actually starts right here on the ground with changing the way we talk to our satellites. The technology is called radio frequency over fiber, or RFOF for short. And here's a simple way to think about it. Normally, if you wanted to send a radio signal over a long cable, you'd have to process it, which often means weakening it. But RFOF is like a magic trick. It just skips all that. It takes the raw, full-strength radio wave and converts it directly into a light signal. And that light signal can then travel through a fiber optic cable perfectly, with no loss. And this is the cool part. You're looking at the actual gear that makes it all happen. This is the hardware. These little boxes do the heavy lifting. They'll take that powerful radio signal coming from a giant satellite dish, transform it into light, and then shoot it for miles and miles down a tiny, hair-thin fiber optic cable with pretty much zero signal loss. Then, on the other end, another one of these devices just turns it right back into a perfect copy of the original radio signal. It's amazing. So, what's the bottom line here? For the ground stations, this is a game changer. It means the links to our satellites are way cleaner, much stronger, and super reliable. We can suddenly handle way higher frequencies, run cables for miles without needing bulky amplifiers, and it's even helping us build out things like next-gen 5G networks. So, we fixed the ground problem. Now, it's time to go to space. Okay, so if that's what we can do on the ground, what happens when we take that same idea, using light instead of electricity, and shrink it down? Way down. Small enough to solve that huge SWAP problem on the satellite itself. And that brings us to this. HIP E. It's a mouthful, I know, heterogeneously integrated photonics and electronics. But the idea is brilliant. Forget all those tiny copper wires connecting different parts of a circuit board. HIP E literally builds a fiber optic network directly onto the microchip itself. It's a network of light on a chip. And there it is. That is how you tackle the size, weight, and power problem head on. By switching from electricity to light right there at the chip level, the advantages aren't just small improvements, they're massive, they're exponential. Check this out. First up, 23 times less energy used. That also means 23 times less heat. And what does that mean? Well, you need smaller solar panels, smaller batteries, and way simpler, lighter cooling systems. Right there, you're saving a ton of weight and space. Next, 19 times lower latency. That's the delay. Data is now zipping around the chip at pretty much the speed of light. Onboard processing becomes ridiculously fast and efficient. And the big one, a 40 times smaller physical footprint. 40. You can cram an unbelievable amount of processing power into a space that's a tiny fraction of what it used to be. It's just staggering. And if all that wasn't enough, there's a bonus. This stuff is just naturally tough. Light traveling through silicon doesn't care about cosmic radiation. It's completely immune to all that electromagnetic noise that can wreak havoc on normal electronics in space. It's built for the job. Okay, so we've got a revolution happening on the ground and a revolution happening up in orbit. What happens when you put them both together? Well, you get a completely new ecosystem for communication, a whole new way of doing things. This isn't just a simple upgrade, it's a total transformation from the tip of the antenna on the ground all the way to the core processor on the satellite. And this is where it gets really exciting, because this unlocks a whole new world of possibilities. We're talking about high-throughput satellites that can beam down incredible amounts of data. We're talking about getting real-time information to the tactical edge, to people who need it right now. It means smarter, more capable, autonomous systems in space. Heck, this is the foundation you need for running advanced AI, and maybe, just maybe, even quantum computing in orbit one day. You know, this quote is a classic for a reason. And yeah, it's a little bit of fun, but HAL 9000 kind of hits on a really important point. When you're talking about these incredibly critical missions, whether it's for national security or exploring the far reaches of the solar system, you absolutely cannot afford for things to go wrong. Reliability is everything. And this new light-based technology gives us a foundation that is so much more robust and secure. So it really leaves you with this one big question, doesn't it? For the last 100 years, all of our progress was built on mastering the electron. Now, we're on the verge of mastering the photon, mastering light itself, from the surface of our planet all the way up to orbit and back again. If our data really does start moving at the speed of light, what new frontiers are we about to unlock? What things that we thought were pure science fiction are about to become everyday reality?